Okay, it's going. So, so just to remind you, the deal here is, and we're going to see this in action in just a sec. So the interpolation thing, the old way to do this is to think in terms of one single polynomial that connects all the dots, and that polynomial might be really ugly, might do something like this. And so with the cubic spline thing, we're connecting the dots in a more intelligent way, trying to sort of match up, make things nice so that we have a nice slope here. And then that's one cubic right there. And then maybe this matches up here, and there's a cubic between those. And the nice thing about cubics is that you can have a point of inflection somewhere so that things get a little smoother. So you end up with a much smoother, much more intelligent function than you might have. So what I wanted to do, ideally, was to code the spline thing, and then I'll tell you my tale of woe. But first, let me just show you on here the picture that you've already made for me in the homework. This is from our Lagrange. So if you wanted to follow along, you could do this. You don't have to have this particular thing, but this is the Lagrange polynomials, if you remember. What we did, oh, here, let's see. I might as well hit enter. There it goes. So we had the Lagrange polynomial. Same thing with Newton's divided difference method. It interpolates using a single polynomial. And so I had this stuff for you to do. And you plotted them. So if you remember, one of the things that we had you do was plot the interpolating polynomials. And you noticed that with some functions, and these functions, the ones that are the bad ones, are ones whose derivatives get bigger and bigger. Because, as you know from your interpolating polynomial days, the error term is going to be related to the nth derivative. So if you have n points, here there's 5 points, the fifth derivative will be, so whatever happens to the fifth derivative, that's what's going to be happening with the error for these things. So the error is related to the derivative. So if I put something like this, that was, oh, that's 7, sorry, seventh derivative. But if I do something ridiculous like 19, so if I have 19 points, then the error for this one is the 19th derivative, but the 19th derivative of 1 over 1 plus x squared gets really, really big, and you end up, whoops, there we are, hit enter, very nice. And you get this massive, like it looks terrible towards the ends here. And it'd be nice if things got a little bit more smooth instead of this ugliness here. I thought it got even worse than this, but apparently not. Now, where'd my cursor go? Oh, there it is. Okay, just a minute. I thought that it was even worse. Let me try the 17th. Yeah, that one's not bad. I mean, -1. It's still pretty bad. It's pretty ugly, but it's not as bad as I remembered. I thought I had it, well, doesn't matter. There's 9 points. Yeah, 9 points isn't too bad. So, so what I'd like to do is to compare this with the spline. So my tale of woe is I went to our book and I thought, yeah, I can do this. I'm amazing, right? And so I took this. Here's the book right here. You can look at it. Joyful tidings. We have this in this octave code. So the main thing, it'd be nice if you could just cut and paste all this right into Python, but that's not Python, that's octave. And so there's some slight modifications. And then the other issue, so there's that issue, is that there's some slight modifications. Not bad, though. Most of this is similar. Get rid of those semicolons because we don't have end-of-line characters for Python. But the main issue that I had was that in octave, apparently, you start counting at 1. And you know how Python is. We start counting at 0. So I ran into major problems with this. But this will give you some joy because since I ran into problems, I decided not to bother coding the splines. And I found, well, I should tell you, confession here. I knew that everything that we're doing is already built into Python. And so I thought, well, at the very least, we can play around with it if it's built in. So like everything we've done, literally everything is built in already. There's numerical integrators, there's numerical, polynomial interpolators. All those things are all built in. So anyway, that's my little mini confession. It's not much of a confession. You probably figured this already, especially since if you haven't turned off your AI thing, the AI thing is, it'd be like, hey, you want to do this? Here's how you do it. It's super easy. But anyway, let's get back to this. So let's just take a look at what would happen if we used the built-in stuff. So give me a sec. So if you have a Python, you don't have to use the one I'm using, although I will superimpose the stuff I'm going to do here with the onto here, just so that we can compare. Yeah, it's so weird that it doesn't look the same. Just a minute. I want to check, because I did this earlier. And I got a fresh, just a minute. I want to just see, where is my stuff here? Okay, just a sec. Yeah, because it doesn't look quite as egregious. Let me look at my there we go. So I did it on a different worksheet or whatever you call it. I feel like that the picture was way worse. No, I guess it's, yeah. I guess I feel like it should look worse, but it doesn't look, it looks just like that. It just, for some reason, it thought it was worse than that. Okay, so let's get here. And so what we're going to do is I'm going to go to a new, sorry, I keep changing windows here and you can't tell what's happening. So I'm going to grab some new code here just to show you what's going on. What we're going to have to do is we're going to have to import. So there are different places that you have these interpolating polynomials, but I'm going to get it from SciPy. So if you haven't figured it out, there's tons of packages for, and if you Google something about Python and doing such and such, linear algebra, whatever it is, you'll find a package that'll work for you. So I'm going to import interpolate. I know there's like interpolators. All the stuff we've done is built in, but there it is. So I'm going to do that. And then I'm also going to, because I had trouble, and I'll tell you in a minute what trouble I had, matplotlib. No, decline. I don't care who you are. Yeah, there we go. Okay, they're gone. I don't know. They can leave a message if they want to. I don't even know who that is. If it was one of my children, I would have answered it. I actually have this memory of being in class pretty early. It was when one of the kids was in college. I think it was at Taylor University, and she FaceTimed me, and her face came up, and I declined. I should have. Yeah. I keep wishing that some child will FaceTime me during class now. So let's see, matplotlib. Yeah, look at me, I can't spell. So it's matplotlib .pyplot. I've been avoiding this. So the whole, let's see, there's NumPy. So NumPy that yeah, you can see, sorry. So I've been avoiding NumPy because it's annoying, and matplotlib, mainly because it seems like the SymPy does a great job doing plots, as you can see right above. That's what I used. However, I had trouble getting SymPy to work with my polynomial interpolator, the cubic splines that are built in. So if I had worked harder, maybe I could have done it, but I gave up. So I have to go back. And this is the way back in the olden days, as in 3 years ago, the way that I used to do numerical methods is we used to use matplotlib a lot, and we used to use NumPy. So if you want to use those things, you go right ahead, but you don't have to. Okay, so there's those. So the interpolate is, of course, the interpolators. The PLT, that's just the plotting, and it allows us to plot things. Okay, so let's see if I can figure out from my notes what I'm going to do. Here's what I'm going to do. So first things first, this is just a little tester. So we have X list is going to be a list of numbers. Let's just say it's 1, 2, 3, 4, 5. And then Y list. So this is your data. Just think of this as your data. So we have something like 1, 5, 2, 3, 3. I don't know. Doesn't matter. This is just to test things out, make sure things are working. So there's X list and Y list. And then what we're going to do is we're going to define splines. X. So this is going to be my splines function. And you'll see how super simple it is. So coefs and interpolate dot split. So that's I'll explain in a minute. X list, Y list. Okay, good, great. So what that does is that, all of those coefficients that are so painful to get, and actually the ones that I would have gotten if I had persevered and done all of this. So this program, by the way, if I actually got down to here, and I was just scared, to be honest, because I had to shift everything essentially, because instead of 1, 1 here, I had 0, 0, and I was just worried after all of this typing. I didn't actually go to the very end, but after all the typing, I was worried that I hadn't shifted something, and it was hard for me to actually evaluate whether I had it right or wrong, and so I just gave up, which is kind of embarrassing, but that's what I did. But anyway, yeah, the coefficients. So here, going down, down, down. There it is. The A, B, C, and D. So here's C, B, D, and the A's, or wherever they are. Anyway, the A, B, C, and D, those are the coefficients for the splines, so that each spline has its own set of coefficients. So there's one A, B, C, and D for this spline, and then another A, B, C, and D, and another A, B, C, and D. And of course, A, B, C, and D, you have 4 of them because this is a cubic. So a cubic spline for each one of those. So that's what this thing is going to do for us once I get back to here. That's what that does, is it computes the coefficients. So they interpolate dot split. And then the last thing to do is just we want to, where is it? Return. Okay, so return. And this is slightly inefficient, but the reason why I'm doing this is so that we can graph things. So yeah, this is super inefficient. Well, sorry, I just realized it's so inefficient. I gotta fix it. Yeah, let's take those coefficients and stick them up here. There we go. That's better. And we'll stick it in here, coefs. There we go. Okay, this is just, you see, the way that I did it in my notes is every time I wanted to compute the value of the splines at a particular point, I was redoing those coefficients, and that's super inefficient. So this will be a little bit better. And then what we're going to return is we're going to return, sorry, interpolate. Oh, here we go. What just happened? I got a little notification that something bad happened. No, nothing bad happened. Okay, interpolate, and then split eve. So that's evaluate coef. Oh, you can't see because of this stupid thing. There it is. Wow, now that is actually feels really dumb. Well, that's the way it is. Yeah, that's really redundant, isn't it? Well, let's see. Yeah, that's really dumb, the way that I've got that. Well, it's okay. Yeah, now it looks really, yeah. I'm kind of embarrassed by what I just wrote there, but too late. Yeah, if you don't see how stupid that looks, then thank you. Okay, so let's go ahead and see how this works. So splines, that's my little stupid redundant function that I just wrote for some strange reason. So let's say I want to evaluate this thing at the point 1.5. Yeah, so dumb. Why am I'm sorry, I'm going to have to shove this in here. No, I guess, yeah, I guess it is what it is, isn't it? Okay, coefs. Yeah, it's so redundant. Yeah, I mean, basically, it's yeah, it's like I've got a middleman here. It's kind of like I don't know. It's just like someone who's going to take a little bit of the computing resources away from me. Feels like that's what the realtor's doing, but enough of that. Okay, so there it is. Oh, array. Interesting. It gives me an array. I didn't realize it did that. Uh, yeah, I wonder if that's okay. Let me try printing that. So this is the actual. Oh, come on. This is the actual spline evaluated. Yeah, okay, that's better. At that point, so I could do this for all sorts of points. So that's the spline between. It's at 1.5. So that's between 1 and 2. I could do this at 1.25, and then I could do it 1.75. Whoops. So each of these that I'm doing now, it's evaluating it between 1 and 2. So it's on that first spline. And then when I go to do this at 2.25, I'm going to get the next spline over. So I could actually make a loop here for I in range. Let's go from 1 to 20. Let's go from 1 to 20. Why does it do that? It's so annoying. Uh, and anyway, let's see, go like this, and then we'll stick this over a bit, and we'll just print splines of I times, let's see, 0.2. So that'll reduce the size of the number. So and I need to be within the range from 1 to 5. So we'll do 1 plus splines. Let's just do that to make sure. So this will give me values between 1 and 3 for the x value, and this will be the y values. So if I hit that, so here this is just, so this is the splines evaluated at 1.1, 1.2, 1.3, 1.4, and so on, all the way down. And so there it is numerically. It's kind of hard to digest those, so let's graph this. So that's the next step, is to graph these things. And so to graph this, did I do yeah, I did do that stuff. So give me a sec. So the next thing that I'm going to do, and then eventually I'm going to put this all together up with my graphing thing. So I need to have, let's see, we'll start with an x value. So we'll just do x, and then we'll do y. Nope. Try again. And then what I'll do is I'll make a loop. So we'll go for 500 points. And then we'll do x dot append. There's different ways. If we were using NumPy, we'd do this a little bit differently, but I'm just used to doing it like this because that's the way we've been doing it this semester. So 1 plus, let's see, how am I going to do this? 4 times I over 500. There we go. So what this is just going to give me a list of x values between 1 and 5. I guess every 100th or so. And then y dot append. And then here I'm going to put splines of x, I, and then coefs. So this is the one efficiency that I just gained by moving my coefficients outside my little thing here. But it's kind of dumb the way I did it. So anyway, if I do that, now I can plot this stuff. So we're going to do plt.plot. So we're using the matplotlib now instead of the one that we've been using, which is the SymPy version. So this is the matplotlib version. And then when we plot this, it's going to print all that junk. So there it is. So there's my cubic spline down there. So it's just kind of neat that you can actually see the cubic spline. All right, so I don't know if you're following along or if you care to or what. I just wanted to make sure that we demonstrated this to see the comparison of this with what we've been doing up till now with interpolating. So I don't know if you have any questions or concerns. Okay, so the final frontier for today. Final frontier is to take what we just did, or what I just did, if you're not doing it, and combine it. I wish I could get rid of that stupid help there. So combine this with this up here. So that's going to be a little bit of a challenge, but it won't be terribly bad. So if you have either your Newton's divided difference method, or this is what I've got is Lagrange polynomials, both of them should work just fine. What you could do is you could just basically copy most of this. So I'm going to copy that stuff and shove it up here. Where is it? Where is it? It's up here. Okay. So I'll stick it at the very beginning. Here we go, where we've got all the rest of the stuff that I'm importing. So I've got all that stuff. And then what else do I need to shove up there? I need this, the coefs. So let's copy that. And I'm going to stick that, though. I know it's back and forth, but so this is my Lagrange. You could do the same thing with, in fact, just to show you, I have what I did earlier today. I'm hoping that this works both ways. My notes, yeah, you can't see it because it's so little, but this is Newton's divided difference method. So I did this with Newton's divided difference method, and now I'm going to see if it works with Lagrange polynomials. It should. There shouldn't be any problem doing it both ways, but we'll find out. So let's see, coefs, where am I going to put those? I'm going to stick them, where are they? Where's it? The graphing. Where's the graphing? Plot Lagrange. Oh, there it is, plot Lagrange. Okay, so it's in this graphing. Just before plotting, I'm going to put this coefs thing. And I think everything's good because at least the way that I did this is I created X list and Y list. And those are the interpolating points. So I've got those. And then I need to go back down. I know, back and forth here. It's going to make you dizzy. I need to define this splines thing, but I'm going to define it locally. Copy. Within the confines of this plot Lagrange. So let's see, put it right here. And I need to, there. So I know this is a little bit weird, but it's like you've got this little subroutine or whatever you want to call it. So I've defined plot Lagrange, and then inside it, I've got splines, which is defined. And it's kind of local to this because I'm using the coefficients. So there, now this is where I'm a little bit nervous that this might not work because of the way I did this. Okay, almost done. Final thing is, because I found that the plotting that we're used to, this stuff, no longer works with, at least not with the splines. I have to go back and I have to use the matplotlib. So here's the way I'm going to do that, is I need to create, basically copy all of this. Give me a sec. Here, this stuff, 1, 2, 3, 4, there. All of that. Oh, might as well go all the way down to there. Copy all of those. And so we're going to put those inside this plotting. There it is. Okay, I promise I won't move it anymore. So paste all that stuff. I need to make sure that I indent everything. So this stuff gets indented here, and that gets indented. There we go. And this gets indented. Okay, we're ready to clean things up now. So let's see, we have Y1. Okay, so just to explain, I'm going to have 3 plots that I superimpose on one another. Y1 is going to be the regular function. Y2 is going to be the interpolating polynomial. Y3 is the splines. So this one is going to be Y1. Oh, no, that's Y3 because that's the splines. And then I just need to create a Y1 dot append, and that one is the function, the actual function. So that'll be f evaluated at xi. And then y2 append is going to be the polynomial Lagrange. So let me do that. Lagrange x list dot y list dot comma x. So I'm just using the same syntax down below. You can see right here. that I have there. Ooh, I need to change one other thing. Now I realize is I need to change this to be A plus B minus A, so that this spans the range of values, whatever values that we want to graph these things for. So I think I've got it all now, and then I just have to put it all together. So we have plt.plot, so that's going to be the original function. Let me get rid of this because we don't need it anymore. And then this one is going to be the interpolating polynomial and then the splines. So let's see if this works. I sure hope it does. Oh, you know what it's going to do? Oh, it's complaining. It's going to complain. What is it complaining about? Convert from what? What in the world? It doesn't like this. Why doesn't it like this? Hold on a minute. Let me just copy that out. Let me see if I can figure out what's going on here. Oh, it liked that. Ooh, ooh, look at that. Those are almost identical. So why doesn't it like this? Huh. X list, Y list. It doesn't like my Lagrange polynomial. Oh, Lagrange isn't defined. Maybe we need to define it up here. Maybe that's my problem. Let's find out. Let me go ahead and print, just a minute, print Y2, because it doesn't seem to like my Y2. Let's see. Ooh, something's going on here. Wow, it's executing. Look at that. Oh, yeah, it doesn't like my Y2. Huh. Oh, I get it. Okay. Sorry, I just realized what I did wrong. Okay, so I forgot that I changed the way that I'm plugging in my X. So X is no longer X, it's XI. And then this should plot well. That's much better. Oh, yeah. Oh, that's so beautiful, isn't it? That you can't even tell the difference. Let me make this smaller so that the number is smaller here. Instead of 9, let's go with 5. So that, oh, that's better. Okay, so with 5, you can tell the difference. So the blue is the original function. The orange is the interpolating polynomial, and the green is the splines. So in this case, the splines aren't much better than the interpolating polynomial, but the reason is that with the splines, you're doing degree 3 polynomials. This is a degree 5 polynomial, so they're really close in terms of their error. But the splines, you'll never get, the error will always get better as you increase the number of nodes. So now we have a degree 7 polynomial, the orange, but notice the green. It's got a little bit of a wave here, but it's doing much better. And then if we go up to a degree 9, they're going to be indistinguishable. The splines, you can kind of see there's the blue and the green, but they're super close to one another. So this is where the splines really kick butt. And if we do the same with our sine curve, I think that's what we have here. You'll find similar thing going on with the sine curve. Oh wait, where you don't even see why don't I see a difference here? Just a minute. Change the number of nodes to 3. Oh, this is going to give me a straight line. 4. Wow, where's the orange? The orange has disappeared. I don't know why there's no orange. Just a minute. Let me get rid of my splines. Okay, there's orange. Oh, is it that the orange and the green are on top of one another? Oh, interesting. That's weird. I feel like that shouldn't be. Let me see. What if I do degree 10? I feel like the splines should be different from the, yeah, this is a sine curve, just a simple sine curve. Wow, they're all right on top of each other. Well, I mean, sine curves are nice. So if I go to 2 pi, yeah, I think I need to give up. But the main thing I wanted to just show you is the idea that the reason why we're interested in splines is so that we can, smooth out those rough areas. Okay, now there's a difference. Okay, so the blue is the actual function. Then the orange, you can see, is definitely closer. That's the splines, very close here. And then the green is the interpolating polynomial. So yeah, you can actually visually see, even though it's a little harder to tell the difference with that as it was with this one. So this one, which is the sort of problematic, the problematic example. So if we go all the way out to, let's do maybe 15 nodes, things are really bad for the orange, but the blue and the green are basically right on top of each other. So that's that. So you can use the built-in splines, I guess, because I didn't bother going through and converting everything. Yeah, I've actually got the splines in a different programming language that I wrote, and I just didn't bother converting. Okay, so what to expect? I think Friday, since the test is the very first, well, it's second test. Does anyone have their test? Does anyone have a test at 8 o'clock, first day? You do? Wait, what class do you have? What time does that meet? On Tuesday? Oh, okay. So you have one. So they put 7:50 Tuesday, Thursday on that. Yeah. What do you think? Oh, it's 8. Yeah. Oh, I was just curious what the very first exam is. Yeah, because it used to be that the Monday, Wednesday, Friday at 7:50 was the first exam of the semester, but so it's apparently that one. You guys are all enjoying that. All right, so ours will be after that. So because of that, I'll try to make sure that I have some sort of a study guide or a material for Friday, and then Monday will be basically optional because we're not going to do anything Monday other than just pick up the pieces from whatever we need to. So that's the plan for the next 2 days, is hopefully I'll get something up. Well, not hopefully, I will get something up for Friday for you for study material. And then, yeah, so if there's any homework you haven't done, that's the Python stuff. So apparently we're not going to have the spline homework due anytime. You can do those as well. So if anyone has any issues with anything, I should probably go through that before Friday as well, so I can bug anyone who has any deficiencies. So any concerns, questions? It's 11:30, or no, it's not 11:30, it's 1:30. So you have time to go get a submarine sandwich, the two of you, if you want to, before differential. I'm going to stop this for